Good evening, everybody. I do want to welcome you to another session of Organic Chemistry Review. In today's session, we are going to use material from Chapter 16, our end of chapter problem set. We do have a lot of material to cover today. By the way, I see Eric has just joined us. Eric, how are you doing? Dylan has also joined us. Dylan, how are you doing? You are all welcome. We do have a lot of material to cover today, so let us start right away. Stephanie, can you go ahead and read this question for us?
Draw the products of reaction of the compound below with Br2 FeBr3. If there is more than one major product, draw both in the same window.
Excellent. Very good. Okay, so what we have here, they want us to draw the product of the reaction of bromine with this molecule here. In essence, they want to perform bromination on this molecule. Here you see the carbon-oxygen double bond attached to an hydrogen atom. So this is an aldehyde group. And also here you have the methyl group in the para position. So this molecule is a methyl benzaldehyde. As you can see also the planarity of the benzene ring. Okay, so what I want to do now, I'm going to take this to my notebook so we could start working this particular problem. By the way, Bria, you are welcome. I noticed that you are joining us. Okay, so this is the problem here. Okay, the first thing that I would need to do here is, of course, to write this problem out for each one of us to start doing the problem together. Now, if I want to ask you, you have the aldehyde functional group, and then you have the methyl group here. Does anybody know what kind of directors each one of these groups have? Let us start with the methyl group. Very good. Somebody has an answer. Yeah, go ahead.
CH3 is an activator, and aldehyde is a deactivator.
Yeah, excellent. Excellent. That's Emma's, yes. So the methyl group is an activator, and the aldehyde group is a deactivator. So given that set of information, what kind of directors are they? What kind of director is the methyl group? Is it an auto-para director or meta-director? Anybody want to give that a try? You could send me a text message if you want. Okay, I see the messages here. Auto-para director. Excellent. Okay, all of you say auto-para director. Okay, how about the aldehyde group? What kind of director is this group here? Meta-director. Great. Okay, so let me write the molecule here. So you have the benzene ring. You have the aldehyde group. And in the para position, you have the methyl group. So the reagent they have given us is bromine in the presence of ion 3 bromide catalyst. Okay, so now the product will be, according to what you guys have told us, the methyl group is an auto-para director, and the aldehyde group is a meta-director. So in this particular instance, which group would direct the incoming group, which will be the preferred director here, the methyl group. Okay, very good. So that means the methyl will direct to the auto position. But it also does happen that the methyl, the bromine goes to the auto position. Bromine goes here. It's just incidentally that the aldehyde group, which is also a metal, director, also direct to the metal position. So it just so happens that in this particular problem here, both of the groups direct to the same position. Okay, is that clear? If it is clear to all of you, give me a happy face. Does anybody have any question on this? Very good. Okay, I see a lot of happy faces here. Excellent, excellent. Okay, so let us move on. This is a fairly simple problem. Let's go to the next problem. Mellard, can you go ahead and read this question for us?
Select the reagents you would use to synthesize the compound below from benzene. More than one step is required. If no third step is needed, leave the entry blank.
Okay. They say if no third step is required, leave the entry blank, which is this here. So because this is supposed to be done in R. Okay. What kind of molecule do we have here? You have this is sulfur. Of course, the red is oxygen. Oxygen attached to hydrogen. So this will be your sulfonic acid group. So this molecule will look like this. That's your sulfonic acid group. And of course, parallel to that sulfonic acid group, you have the bromine atom here in the para position. So you have bromine here. Okay. So now what do they want us to do here? They want us to choose any one of these reagents here to synthesize this molecule here, starting from benzene. So let us see what we can do with this. We have to start from benzene. Okay, so we have benzene here. We have benzene. Now, let me ask you this. This is the product that we are supposed to make. Taking a look at this product here, what kind of director is the sulfonic acid group? Anybody has an idea? What kind of director is the sulfonic? Okay, metal director. That's Eric. Excellent. Sister say metal director. Michael. Great. It is a metal director. How about the bromine? What kind of director is the bromine? Auto para director. Now, so now this is the problem we have to solve. We have the bromine and the sulfonic acid group. They are a 1-4 relationship to each other. In other words, para to each other. Okay, now in order for us to make this molecule, therefore, what do we need to do first? Okay, do you want to do the bromination first or the sulfonation first? Which step do you do first? Excellent. Eric said bromination. Okay, great. That is correct. But can you tell me why bromination first? Why do you want to do your bromination first? That is correct, by the way. Why the bromination first? Okay, you said bromination because... Okay, great, great. Bromination because the sulfonic acid group is because the sulfonic acid group has to be a metal director. So, therefore, if you want the para product, you have to do bromination. Keep in mind that the bromine is an auto para director. Okay, so we do this. So we get our bromine here. Okay, so that means the next step, therefore, we now do our sulfonation reaction, in which we use sulfur trioxide in the presence of sulfuric acid. Okay, so where are the reagents here? The reagent they gave us is this here. Okay, where are the reagents? You have A. That is the first step that we've taken, which is this here. And then the next step is sulfonation, which is this. And that will lead to the product. Okay. So, folks, the point to be made here is you need to know the sequence, the appropriate sequence for these synthetic processes. Because if you do not know the appropriate sequence, which of course will be based on the type of directors you have in your molecule, then you will be wrong in your conclusion as to what the product, the sequence should be. So, in this particular instance, the correct sequence will be bromination followed by sulfonation. Okay, is that clear to all of you? Okay, okay, very good. So, if it is clear, give me a happy face. Okay, a lot of happy faces here. Okay, good, very good. Okay, now let us now go to problem number 4 here. Okay, Sean, can you go ahead and read this for us?
Rank the compounds in each group according to their reactivity toward electrophilic substitution.
Okay, great. Okay, so what they want us to do here is to rank these compounds here in this group, group A and group B, according to their reactivity toward electrophilic substitution reaction. Okay, so the first thing I want to do here for A, I am going to write the structure. So you need to know your nomenclature here. So part of what is being tested here also is your nomenclature. So toluene, okay? So you need to know what toluene is, which is the benzene molecule attached to a methyl group. That is your toluene. And then the next one, methoxybenzene. Methoxybenzene, of course, is this molecule here. So, folks, you need to know your nomenclature because this is just pure memorization at this point. That is methoxybromine, methoxybenzene. This is your methoxy group. Okay, so we've done that. Then you have the fluorobenzene. Does anybody know what fluorobenzene will look like? What is fluorobenzene? Can you describe fluorobenzene for us? Okay, fluorine attached to benzene. Excellent. Fluorine attached to benzene. Okay, very good. So you guys have just told me that fluorobenzene is this here. So therefore, they want us to determine to rank these compounds as based on their reactivity towards electrophilic aromatic substitution reaction. Number 1 being the most active. Okay, so where is number 1 here? Which is number 1? Can anybody tell me which is number 1? Okay, number 1, methoxy. Excellent, methoxy. Methoxy is a very powerful activating group, so therefore methoxybenzene will be the most active. Now, which will be the next one? Toluene, excellent, number 2. And then, of course, naturally, the fluorobenzene will be number 3. Okay, so that is correct. Now, let us do B. Let us go to B. B, okay. So for B here, you need to also know the names of this here, benzonitrile, that is this molecule here. Benzonitrile is benzene attached to a cyano group, which is carbon-nitrogen triple bond. So we could call this cyanobenzene. The common name is this here. This is the common name for that molecule, benzonitrile. Okay, now you have p-methyl benzonitrile. Now, what will p-methyl benzonitrile look like? P-methyl benzonitrile, what will it look like? We already know what benzonitrile is. Okay, so the methyl group will be in what position of benzonitrile? This is benzonitrile. Okay, in the para position. Okay, great. Okay, so that is benzonitrile. And then they say p-methyl. So methyl group is in the para position. Okay, or the fourth position. Now the next one is p-methoxy benzonitrile. Yeah, go ahead. Somebody has a question for me? Okay. Okay, so now we have this. Okay, I see Jasmine is joining us. We have benzonitrile here. And then we have the methoxy here. Okay, so let us rank this according to what we have here, which is the most reactive towards electrophilic aromatic substitution reaction. Number 1 being most reactive. Okay, which is number 1 here? Which is number 1 is p-methoxy. Excellent. P-methoxy. Okay, good. So p-methoxy is number 1. Okay, where is number 2? Okay, where is number 2? Where is number 2? Methyl. Good, good. That is correct. And naturally, this will be number 3. Okay? Okay, if that is clear to all of you, give me a happy face. Okay, there is no frowning face. Okay, very good. All happy faces. I see a lot of people have joined us tonight. Avery, you are welcome. I see you join us. Brandon, you also welcome. Go to the next one. Okay, Julianne, go ahead and read this question for us.
Draw the major products of electrophilic chlorination of M-methoxybenzoic acid. Okay, so they want us to draw the major products or products of electrophilic chlorination of M-methoxybenzoic acid. Okay, so the first thing is we need to know what M-methoxybenzoic acid is, and of course we know this is benzoic acid. That is benzoic acid, which is a carboxyl group attached to the benzene ring. So now the M-methoxy will be this here, the methoxy in the meta position. Now they want us to, oh, my pen just moved. Okay, now they want us to do chlorination. Which is this reagent here. Okay. Now, where would the chlorine go? where would the chlorine go? Maybe the first question I need to ask you, which of these groups would direct the incoming group? The methoxy group or the carboxy group? The methoxy, exactly. The methoxy. And therefore, the methoxy is what kind of director? Anybody know methoxy, what kind of director? Auto-para director. So, okay, do you expect the the chlorine to go here? Yes or no? If no, why? Why not here? That is an auto position. Because of steric hindrance. Excellent. Because of steric hindrance. Steric hindrance. Okay, good. So we do not expect the chlorine to go here. So therefore it will either go here or here. So we are going to get two products. So most of what we are doing so far is knowing what kind of director you have in this molecule and also knowing your reagents. Okay, so we have that here. We have the methoxy here. And of course the chlorine will go here. That is one product. The second product will be the chlorine going to the para position relative to the methoxy group. Okay, so you have that here. That's here. And then, of course, this is the para position. Okay, is that clear to all of you? If it is, give me a happy face. Okay, somebody asked a question. Go ahead, Emma.
Would that other product not show up with the other ortho product, if possible?
Mean the auto here, right here?
Yes.
Yeah, if it shows up, it will be very small. It would not be a major contributor to the product. So generally, whenever you have a steric hindrance, in this particular instance here, the incoming group does not want to go here. So it will be very small. So I will consider that as not to be included in your product mixture.
Okay, thanks.
Okay. Okay, so let's go to 6. Okay, now Emma, go ahead and read this question for us.
Predict the products you would obtain from sulfonation of M-xylene.
Okay, M-xylene. Okay, this is another common name. But M-xylene is this molecule here. These two methyl group attached to benzene. You have a methyl group here. And since they say M, another methyl group here. I notice that Sean is just joining us. I'm sorry, Sinead is joining us. You are welcome. Okay. So now they want us to give the product of sulfonation. So the product of sulfonation. Okay, so what will be the product? What product do you expect? Let me, just for reference, let us say this is position number 1, position number 2, position number 3, 4, 5, and 6. So, for sulfonation, you need to know what reagent do we need for sulfonation. Can anybody tell us? What reagent do we need for sulfonation? Okay, A2SO4, excellent. A2SO4 plus SO3, excellent. Sulfur trioxide and H2SO4. Folks, you need to know your reagents. Remember, I kept telling you from the last semester, knowing your reagents is the beginning of knowing organic chemistry. Okay. So now, this sulfonation here, where do you expect the sulfonic acid group to go? Where would the sulfonic acid group go? Will it go to position 2? What position will it go? 4, 5, 6. Okay, 4. Okay, good. Because that is an auto para director. Yes, we will expect something there. Right? So we will expect this here. This here. I see Jamie McPherson also joining us. You are welcome. As we progress during the course of this session. Okay, now let us take a look at this here. Does anybody have an idea what this will be? By the way, Ambre, go ahead and read this for us. I notice your internet is acting up. Yes.
It says,
go ahead.
Draw the major products of the following reaction.
Okay, very good. Okay, I saw you coming in and out. Brandon, go ahead, ask your question. Jasmine, go ahead.
On the previous question, you added a methyl group when you reacted with the sulfur reagent.
Oh, did I do that? I'm sorry. Oh, did I do that? I'm sorry. Oh, thank you so much. Oh, thank you. You guys should remind me. Yeah, I'm glad you brought that up because I do not want that to go without us correcting that error. Supposed to be sulfonic acid group. Good. Folks, please do not hesitate to let me know if I make a mistake while we're doing this, because I have so many things going on, looking at the text messages, looking at you coming in and out and all that kind of stuff. So anyway, that is correct, Brandon. Thank you so much. So this is the product. This reagent here, what it does is to replace hydrogen of the benzene with the sulfonic acid group, and that is what we expect to get. Okay. Now, okay, about this one here, what will be the product here? Okay, let me give you a hint. Remember in the class yesterday, carboxylic acid, excellent. Okay, that is why I wanted to give you a hint. Now, if you have carboxylic acid is correct, but there is something that I also want you to know. If you have an alkyl group, any alkyl group attached to benzene, it does not matter how long the alkyl group is, as long as the carbon that is attached to the benzene, as long as it contains an hydrogen atom, that alkyl group, when you use potassium permanganate, whenever you use potassium permanganate, generally in acidic medium or in water, as is in this case, what you're going to get, the alkyl group will be oxidized so that the carbon that is attached to the benzene ring becomes a carboxyl group. Okay? That is provided there is an hydrogen attached to this carbon here. If on the other hand, I have this. If I have this, if I have this, if I have this, if I have this, okay, okay, since there is an hydrogen attached to this carbon, if I do this, potassium permanganate, in acid or water, you get benzoic acid, okay? It becomes a carboxyl group. So far, so good. Now, If on the other hand, if I have this, if I have this, and you do not have an hydrogen attached to this carbon here, and you have the same reagent, potassium permanganate, water or acid, there will be no reaction. Okay? Keep that in mind, no reaction. The only time when you have this carbon, which is attached to the benzene ring, the only time it will be oxidized to the carboxyl group is when that carbon is attached to hydrogen. Okay, now that we've given you that bit of information, let us now come back here to answer this question. So what will be the product here? I see Sholanda is just joining us. You are welcome. What will be the product here? Okay, let me help you out here. What will be the product? Okay, no reaction on this here. How about here? How about here? Would there be reaction on this carbon? Yes, there will be reaction on that. So therefore, what product do we expect? So therefore, the product will be this. You have your methyl group, all of this still here, nothing happens here. Okay, and of course here will be your carboxyl group. Is that clear? Okay, now supposing I have this. Supposing I have this. Supposing I have that, what will be the product? Two carboxyl group. Okay, one on this side, because this will be oxidized to carboxyl group, and this carbon will be oxidized to carboxyl group. Great, great. Okay, very good. Okay, very good. Okay, so let us go to the next one. Okay. Dimitris, go ahead and read this question for us.
Select the reagents you would use to synthesize the components below from benzene. Use the minimum number of steps.
Okay. What they want us to do here, to select the reagents that we are going to use to synthesize this compound here and this compound, M-chlorobenzoic acid and 1,3,5-trinitrobenzene. Okay, they want us to choose from here, this reagent here, all of these reagents here. Okay, of course we have to start from benzene. So let us try the, okay, 1,3, let's give the structure of 1,3. The first thing, of course, you need to know the structure of the product that you have to make. So that is this here. (1,3,5) trinitro, so nitro here, 3 nitro here, 4,5 nitro here. So that's 1,3,5-trinitro. They also want us to make this compound here, benzoic acid, of course, which will be a derivative of benzoic acid. That is benzoic acid, and they say M-chloro, so that means the chlorine atom is here. Okay, that is what they want us to make. Okay, so let us start with the first one. This one should be fairly simple. Okay, does anybody know how to make this here from benzene? From benzene, okay, CCC. Okay, great, great. Somebody said nitrogen, excellent. So in other words, you guys want us to use excess of this here, excess of the nitric acid in the presence of sulfuric acid. If we do that, then we expect to get this product. Keep in mind, when you do the first one, this sulfonic acid group is a metal director. So the next one goes to the metal position. And of course, the next one also goes to the metal position. So that's a fairly simple process indeed. Okay, so we get that. Okay, do you see that? If you see that, give me a happy face. Oh, jumping. Yeah, I got it. Yeah, Sinead, thank you. Okay, that is nitro. This is what we need to make. It's a metal director, and metal director. Okay, thank you. That was Sinead, very good. Okay, so now you get this product here. That should be fair. That should be fairly simple. Now, how about this one here? How do we go about making this? We need to do a little bit of analysis here before we can do that. How do we go about making this? Okay, the question that I have for you is we have to make M-chlorobenzoic acid. Do we know any reagent that would directly add carboxyl group to the benzene ring? Do you know of any? No? Very good. Okay, so what do we need to do? Keep in mind, this is a metal director, this is an auto para director. So what do? We have to add an alkyl. Excellent. Okay, very good. If we have to add an alkyl, do you want us to add the alkyl group before we add the chlorine? Both of these are auto para director. The chlorine is the auto para director. The alkyl is auto para director. Okay, so let us try that. Okay, let us see. We want to add the alkyl group. Okay, we take benzene. Take benzene, so we're going to perform a Friedel-Crafts alkylation. Okay, that's what we want to do now. So therefore, we could use methyl chloride in the presence of aluminum chloride. Okay, so if we get this, Now, what is the next thing we have to do now? Because keep in mind now we need to introduce the chlorine, and what you have here is an auto para director. Okay, so okay, great. You guys say we now have to do oxidation. Excellent. So now once you do your oxidation, which is potassium permanganate in acid or water, that will give you your benzoic acid. And now once you do your benzoic acid, what do you do now? What do you do now? Chlorination, because the carboxyl group is a metal director. Very good. So now we could do chlorination. So once you know the type of orientation of the substituent that is attached to the benzene, in other words, what kind of directors are they, then this becomes very simple for you to do. Okay, so now we get our product. Which will now be, okay, well, I was going to draw a long arrow to here, but let's go ahead and just draw it out, and then you have the chlorine here, because the carboxyl group is a metal director. Okay, is that clear to you? If it is clear, let us see what reagent do we have here. Do we have these reagents here? Okay, where is, okay. So this is D. This is D, which is this here. And where is this here? Do we have this here? Yes, we have. This is F. Okay, do you have the chlorine? Yes, we have the chlorine, which is B. Okay, very good. Okay, very good. So now let us go to the next one. We are moving right along. Okay. Okay, let's see. I have not talked to a lot of you. Let me see who. Bria, is your mic working? If it's not working, can you read this question?
The following synthesis scheme is flawed. Draw the actual product that would be formed by the scheme.
Okay, very good. So what they say here, the synthetic scheme that they have given us is flawed. In other words, something is wrong with this. So they want us to now draw what the actual product will be. Okay, they say draw the actual product that will be formed by this scheme. Okay, let us do the first one. The first thing here, okay, what type of reaction is this, the first one? Anybody know? Okay, acylation, free-to-crab acylation, exactly. So, we have this here. So, we have free-to-crab acylation, in which you have this attached to benzene. Okay, so that is the first step. Very good, so far so good. Now, what is the next step? Does anybody know what the next step is? Another, yeah, go ahead. Okay, what is the next step? Another free-to-crab alkylation, okay? So now they want us to do this. Okay, folks, and now I will tell you something that I did not get a chance to tell you in class, and that is free-to-crab alkylation or free-to-crab acylation do not take place whenever you have electron withdrawing group attached to benzene. In other words, anytime you have a metal director attached to benzene, Friedel-Crafts alkylation or Friedel-Crafts acylation does not happen. So this reaction would not go. Okay? Keep that in mind. In other words, if I give you this, supposing I give you this, if you look at all of the deactivators, all of those that we call deactivators, if I give you this and I say, okay, this reaction here, what is the product? Okay, you have to tell me no reaction. Okay, so keep that in mind. Do not forget that. I forgot to tell you in class. Okay, so Friedel-Crafts alkylation and Friedel-Crafts acylation do not take place whenever you have electron withdrawing group or deactivators attached to benzene ring. Okay, the only deactivator that will undergo Friedel-Crafts alkylation and acylation are the halogens, and keep in mind that those are just moderate. Those are moderate deactivators. But the very serious deactivators do not allow Friedel-Crafts alkylation or acylation to take place. Okay. Okay, so therefore we say this is wrong. So if that is wrong, so what will be the product of this reaction?
Did you say moderate deactivators
yes.
will let the reaction happen?
Yeah, I mean the chlorine, bromine, all the halogens, yes, Friedel-Crafts alkylation will work with those. Okay,
yes,
that's clear? Okay, very good. So now, since there is no reaction here, okay, so what we expect to obtain here is that once you perform the first step, then the next step, or the third step, which will be this here, which will be sulfonation. Okay, so the product that I will expect to obtain will be what? What kind of director is this here? What kind of director is this? Metal. Okay, so in this particular instance, therefore, I will expect to obtain because this ketone group is a metal director. Okay, so that is what is going to happen. The reason why we get this product here, because at this point nothing happens. Nothing happens. Okay, and that is why we have no reaction. Okay, if that is clear, give me a happy face. Okay, good, good. Let's see, what time do we have? We have 7:50. Okay. Let's see, we could go a little bit over 8. Okay, we've been here now almost 1 hour. Okay, now. Let me see. Yeah, Jasmine, go ahead.
In that last problem, wasn't another step to get the CH3 that was on there?
Let's see. The last one, okay, that was 10. The CH3, where you say CH3, this one here?
The product that they gave me.
Yeah, what? Okay, yeah, okay, I got you now. Very good. Remember what they told us? Remember what they told us, that this process here is flawed. That's what they said. In other words, this reaction will not happen the way it is written. So therefore, this is not good. You see, if this Friedel crab has happened here, then you expect to obtain a metal here. But because we say the Friedel crab alkylation will not happen here in the second step, so therefore we do not expect to get any metal in this molecule. Do you follow that? Okay, very good. Okay, so therefore we go back to this. Okay, Jasmine, go ahead and read this question for us.
Electrophilic substitution on 2-nitrovinyl benzene occurs at the meta position. Draw resonance structures to show how the ring is electron poor at the ortho and para position.
Okay, now this is a little bit more difficult problem. By the way, I noticed that Jessica and Olufunke they have just joined us. Both of you are welcome. Okay, what do they want us to do here? They said electrophilic substitution on this molecule here occurs at the meta position. In other words, what they are telling us that this group is a meta director. Okay, it is a meta director. If you recall, when I told you in class that when you have the carbon-carbon double bond attached to benzene, that would be an auto-para director. But in this particular instance, what they are telling us is that this particular molecule here, this group, is a meta director. Now they say, okay, they want us to show why it is a meta director by essentially showing that if an incoming group goes to the auto position or the para position, that the reaction would not be likely. Okay, so let us see what happens. We are going to draw this molecule here. In other words, what they are asking us here, we need to know the reaction mechanism. Okay? In essence, they want us to draw some kind of reaction mechanism involving this molecule. So you have this. Keep in mind you have the nitro group. Is this here? This is your nitro group. Now they say, supposing an incoming group goes to the auto position or para position, show how this will not be favored. Okay? Now let us now have some kind of electrophile. Let us use a generic electrophile. Let us just say E for electrophile. Okay? And what will happen? At this point, let us assume that this reaction, it will go to the electrophile goes to the auto position. Okay? Let us do that. If it does that, what are we going to get? Sinead, go ahead. Sinead, you have a question? Go ahead and text your question to me. Okay, while we're waiting for Sinead. Oh, okay, very good. Okay, so what do we get? We have this. This is one of those questions that you just have to understand exactly what the reaction mechanism is before you could actually attempt this question. Okay, so you have the double bond is here, double bond is here, and this is here. The nitro is here. Okay, so if we now say, of course we know the hydrogen is here. This hydrogen was here before, so it's still here. So we now say the electrophile is here. Okay, if that is the case, keep in mind also we have hydrogen here. We still have the hydrogen here. So now the positive charge is here. Now, let us now draw resonance for this. If we draw the resonance structure for this, okay, let's draw the resonance for this. We move this to here. Okay, so if we do that, the positive charge will be here. Okay, so that goes here. That means the positive charge is here. This is still here. And then this is here. The nitro is still here. Okay. Now here, what do we have? We still have our hydrogen here, and our electrophile here, and of course this hydrogen is still here, just to keep everything in, keep our good bookkeeping here. So now we draw another resonance. If we draw another resonance, we will move this pi electron to here, so that means the positive charge will be on this carbon now. Now follow this very closely now. Okay, was this problem similar to what we did in class yesterday? To some extent, yes, it is similar. It's just yes, you are correct. It is similar to what we did yesterday. If you understand what we did in class yesterday, then you will understand where we're going with this, okay? Okay, so now we have that. So we move that to, this double bond is now here, this is now here, and now the positive charge will now be here, and this is still attached to this, okay. It is similar to it with a little bit of nuance to it, just a slight difference, a slight variation of that problem. Okay, so now you have hydrogen still here, and this is still here, and our hydrogen is still here, but we don't want this getting crowded here, so I will not write the hydrogen here. Now, this is where the problem now comes. If you now have your positive charge on this carbon, which is conjugated with the double bond, okay? So now we're going to write another resonance. Okay, when we do that resonance, we are going to move this double bond to here, so that it will be double bond here, and when we do that, there will be a positive charge on this carbon. So follow this very closely, because that is the essence of this question. That is what they want you to know. Okay, so now we have this. As you can see here, it's similar to what we did yesterday, but with a slight difference. But if you understand what we did yesterday, then you will be able to do this. Okay, so we have this here. We have this. Now the double bond will be here, okay, because of this resonance here. And then we have this here. Now, this carbon now becomes positively charged. Now you now have nitrogen is still here. Let me now put the oxygen here so it not crowd that place up. Now, you see where the problem is. Anytime you write a resonance structure and you have two positive charges next to each other, that is a terrible resonance structure. That is very destabilizing. So therefore, that is why this group, instead of being an auto-para director, it will be a meta director. Because when it directs the group to the meta position, you do not obtain a destabilizing resonance structure just as you have here. So that is the essence of this problem. Okay? Do you follow that? If you do, give me a happy face. Okay? So it is, I mean, you really do need to understand this, because if you do not understand the mechanism of electrophilic reaction and you do not understand resonance, you will find this problem very difficult. This is not one of those problems you simply just memorize. You really do need to understand what is happening. So anyway, the point here is, when an incoming group goes to the auto or para position, you obtain a very destabilized intermediate carbocation. But if you go to the meta position, when you go home, try to write this so that you put the incoming group in the meta position, just here. Then you will find that you will not get a destabilizing resonance structure, just as we have here. In this case, you have two positive charges next to each other. That is not good. Okay? Okay, so now let us go to the next one, number 16. Okay, this is another mechanism reaction. Okay, we're getting to the end of our session today. So you notice we are gradually increasing the difficulty of these problems. Okay, let's see. I need to get somebody here. There is your mic working. If your mic is working, can you read this question for us? How about Courtney? Is your mic working? If it is, read this question for us. Okay, let me go to somebody I know the mic is working. Bria, go ahead and read this question for us.
Benzene reacts with 2,2,5 tetramethyl tetrahydrofuran as shown below. Draw a structure for the electrophile that reacts with benzene.
Okay, very good. This is another very good question that requires that you know the mechanism of electrophilic aromatic substitution reaction. If you recall, the basis for all of this reaction is that you must form, the first thing that happens, you will form an electrophile. Okay? In all of this reaction, an electrophile is formed. So what they are telling us here, this molecule reacts with benzene to form this molecule in the presence of sulfuric acid. And what they want us to do now is to show the electrophile that is formed. Now, if I ask you this, just taking a look at this here, look at this carbon here. Okay, look very closely now. This carbon here is this carbon. Okay, so what does that tell you as to where the electrophilic carbon will be? In other words, we have to form a carbocation. So where would that carbocation be? Will it be here? Will it be here? Okay, if it is here, yes or no? Will it be here? Okay, they say no. Okay, will it be here? No. Will it be here? Will it be here? It has to be somewhere now. The carbon, look at what we have. Look at the product. This carbon here is being attached to benzene, is replacing the hydrogen. So what does that tell you about this carbon? This carbon must be the electrophilic carbon. That is what that is telling us. Okay? This must be the electrophilic carbon, the carbon that was positively charged. In other words, the carbocation. Okay? So once you recognize that, then you want to form the carbocation. Okay, so how do we do that? Okay, we say we have this molecule here. Keep in mind, this is oxygen. Oxygen has non-bonding pair of electrons. And then you have acid here, okay? So you have the acid. Acid contains a proton. Okay, so what will happen? This oxygen, of course, will attack the proton, will pull the proton from the sulfuric acid. So that oxygen becomes protonated. Once you do that, then we have this. We have this here. Okay, so now you have the proton here. This is similar to water being protonated, similar to protonation of water, in which you form hydronium ion. If you recall, we have hydronium ion. We could do that. So if we could protonate water to form hydronium ion, and this becomes positively charged. That is the same thing that is happening here. So now this now becomes positively charged. Think of this as hydrogen, think of this as hydrogen, and then you protonate the water. Okay, anytime you have a hydroxy group, they are easily protonated by an acid. Okay, so once you form that, this protonated ether here, because this is an ether molecule right here. If you recall when we did inorganic 1, okay, so we protonated the ether, and then what is going to happen? It's going to open up this here, because what are we going to do? We are going to form a stable carbocation. Because now if it breaks this bond here, this carbon-oxygen bond, if it breaks, you are going to form a carbocation on this carbon here, which is a tertiary carbocation. So we have this. So now we have this. Okay, positive charge is here. Now the oxygen becomes this here, breaks away, so now we have this here. Okay, now what do you think is going to happen? This carbocation now is now going to attack the benzene. Okay, keep in mind, all they're asking us to do is to draw the structure for the electrophile. That is all they are asking us to do here. But let us go a step further. Okay? Once you form this electrophile, this is the answer they are asking for. In other words, what is the electrophile? This electrophile, this carbon now, will attack benzene. So we have benzene here. Let us draw this. Think of this as just a regular E plus, okay? Okay, do not be intimidated by the fact that this molecule looks fairly big. Nothing but E plus. Think of it as E plus. Okay, if that is the case, we have, just like any E plus, this here coming here, attacking this here. Okay, and also we know that we have hydrogen here, right? So if that is the case, what do we get? We get this here. Okay, so we get that. We have this here. Let us have this here. Let us have this here. Now we say we have hydrogen here. We have our E plus attached to that. This is here, and now this is here. Okay, so now we have this carbon, which is this here, another carbon here, which is this here, another carbon here, which is this here, and then you have the OH. Okay, so let us do this right, okay? This here, this carbon is this carbon right here, okay? Of course, the positive charge will be here. Now, this carbon here is this carbon. This carbon here is this carbon. Okay, I think I'm running out of highlighter. Okay, so yes, this one here. This carbon here is this carbon. Okay, so you now form that. And once you form that, what do you now have? What do you have? Keep in mind that in this case, you have, when we did this, we also formed because that's sulfuric acid that we use. I'm sorry, this should be 4. Okay, so we also have 4 H2SO4, 1 hydrogen. It is negatively charged because keep in mind that we put away proton, and we therefore have this here negatively charged right here. So now this will act as a base. Will now act as a base to now come here to pull this hydrogen out of here, and now you are going to regenerate the ring system. You regenerate the ring system. Now we form our aromatic ring system again, and this is still here, this is still here, this is here. Now you have this here, this is here, this is here, and now this is also here, and this is here. Okay, keep in mind, let us keep track of our carbon here. This carbon here is still here. This carbon here is still here. This carbon here is still here. And this carbon here is still here. Now, do you now see what is going to happen? The next thing that is now going to happen, keep in mind, the question is, how did we get to here? Now, the next thing that will happen, let me make some room here. This is the question of the day, by the way, in case you guys have not noticed that. Okay, so the next thing that will happen, because now if somebody tells you to explain how you go from here to here, okay, how does that happen? Does anybody now know how that happens? What is the next thing that will happen if we have to go to here? Keep in mind, I'm sorry, I've been losing my, okay, let's see. Somehow I lost this. Okay, let's see. Okay, this one here, okay, this will be here. I lost my 2 methyl group. Okay, I lost my 2 methyl group. Methyl is here, and this methyl is here, Okay, now, sorry about that. Now, how do we go from here now? Can anybody tell me how do we go from here to the final product, which is this here? Can anybody tell me how that happens? Anybody has an idea? What will be the next step? Keep in mind, sulfuric acid is still in the solution. Anybody has an idea? I will give you a hint. We have just done this. Okay? Look at what we did before, exactly. The O8 gets attacked by the sulfuric acid. In other words, what we are going to do now, we are going to repeat this process all over again, in which sulfuric acid comes here, Okay, attach this hydroxy group. Once you do that, what do you get? You now get this. You have this here. Okay. Okay, so now that gets protonated. You protonate now we are going to protonate the alcohol. Once you protonate the alcohol, keep in mind that you have a methyl group here, then what happens, you're now going to lose, just as we lost this here, this breakaway right here, now here we are going to lose the water. And once you lose the water, you now form a carbocation right here. Now another tertiary carbocation, by the way, let me have this here. See here. So you're now going to form another tertiary carbocation. Now we have this here. This is here. This is here. Now we have this here. Tertiary carbocation. Now, what do you think is now going to happen with this tertiary carbocation? What is now going to happen? Keep in mind we also form water because we are losing this. What is now going to happen right here? Okay, exactly. Now, this is now another electrophile. So this is nothing but another E+. Okay, that is another E+. So now let us now finish the process. Another E+. So we now have the electron here, comes here, attach this carbon. Once it attaches that carbon, what do you think will happen? We now form the ring. Now we're now going to have this here. As the electrophile, exactly, it acts as the electrophile. So now you have this. Okay, so now you have this here. Okay, hydrogen is here. Keep in mind you have hydrogen here. And so therefore the positive charge is here because we are using this electron here, this pi electron here. And keep in mind the hydrogen is here originally. So we see have that hydrogen is here, right here. And this one is still here. This is here. And this is still here. Sorry, and this is here. Now, what happens? This water that we lost here will now act as a base. That water will come in here. Okay, Kia is just joining us. Kia, you are welcome. Okay, so now that water comes in, act as a base, come to pull off this proton here, and then you now have your, and guess what? We now form our product. And that is this product right here. Okay, now do you see how we get from here? Let me erase all of this here. You see how we get from here? Take this out. So if somebody asks you to write a mechanism for a reaction similar to this, you're going from here to here. In other words, the essence of all of this is we are forming, it's almost as though we are doing two different types of alkylation. It is a variation of Friedel-Crafts alkylation. But instead of using an alkyl chloride or bromide, we are using this alcohol here, or ether. But the point is we are going to form a carbocation here, which is what you form when you perform Friedel-Crafts alkylation. That carbocation is attacked by this, and then the next step, another carbocation is formed again, and it's attacked by this, and then we end up forming our final product. I know that is a very, very long one, but this is one of those questions that you really do have to think, and you really do need to know what is happening before you can solve this problem. Okay, is that clear to you, or do you have any question? If it is clear, give me a happy face. If it is not, give me a frowning face. Okay, I see a lot of happy faces. Okay, very good. I see. What time is it? It is about 8:22. Let's see if I see a very simple problem. That's too much of a, no, we don't want to do that. Let me see here. Simple one. No, that is difficult problem too. So, okay. 20. Okay, let's see this here. Okay. Okay, let's do this and then we call it a day. Oh, I think we did this already, didn't we? No, this is, oh, no, okay, this is fine. We didn't do this. Okay, let's do this again. Can I get somebody to read this?
The following
Emma, go ahead and read this for us.
Draw the actual product that would be formed by this scheme.
Okay, very good. In other words, they are telling us, just like the one we did previously, that this synthetic scheme that you are giving here is flawed. Okay? So let us see what the synthetic scheme is supposed to give us. Now they say, draw the actual product that will be formed by this scheme. Okay. Let's do the first one. What does the first one give us? What is the first one?
Acylation, which is
what do we get in the first
one? As a ketone, right? As O to CH3.
Acylation? Yes. Okay, good. Oh. Yeah. Okay, great. Okay.
And then that would add on to
okay, very good. That is correct.
And that one's going to add two hydrogens, which probably for O.
No, it's wrong. This only has to be done right. That's somehow that's wrong.
Okay, I do, yeah. Okay, turn your mic off. Okay, so we have this here. Okay, so we are going to perform Friedel-Crafts acylation, and in this case, the methyl group is directing to the the para position. Okay, so that is this here. That is step 1. Okay, so step 2. What do we have in step 2? We have, what kind of reagent is this? Step 2, what kind of reagent, what does it do? Nitration, okay, excellent. Nitration. Okay, so what do we expect as the product? Okay, nitro group, okay, good. So we expect, in this case, the methyl is an auto-para director, and of course, it will take over the direction. But in this particular instance, it does not really matter because this group here is a meta director anyway. So we are, okay, so we have that. Now, what is the next step they've given us? What is the next step they're giving us? They're now giving us hydrogen and palladium. Okay, so what is the product you expect to get? What is the product they expect? This is what they said we are going to get. Hydration does not work on rings. Hydration, oh, okay, I see. Hydrogenation, okay. Okay, does not work on rings. Okay, now what is the product you are supposed to get? According to them here, this is what they're telling us, that this carbonyl will be reduced to a CH2 by this reagent, which is okay. But what is the problem with this process? If this is what they are using, what do you think? Why is that a problem? Why do you think that is a problem? This will reduce the carbonyl to CH2. There is no problem with that. But what other problem are you going to have with this? Anybody see that? It also reacts with NO2 exactly. The problem with this is this reagent also reacts with NO2 to turn to NH2. So therefore, this will not work. If this is what we do, this is the product we are going to get. If we do that, this is the product we are going to get. So that is why this process is flawed. We will get this. We will get that, okay, no problem. But here, this becomes an NH2. And of course, you still have your CH3 here. Okay, now the question I ask for you, supposing this is the product we really want. Supposing this is the product we really want. What reagent are we going to use in this third step? Supposing, oh no, that's not okay. The question that is not okay. I take that back. That would be a very difficult one. Now, what I was going to ask you, that supposing we wanted to reduce this without having to touch this. Anyway, so in this particular instance, this is the product you are going to get, okay? Now, the question I also do want to ask you is, supposing I want to go from here, okay, this is what I want. I want you to tell me what reagent should I use. I see I have this here. I have this here. And then I have this here. NH2. So what reagent do I need to use to go from here to here? Anybody has an idea? Oh, okay. Oh, you knew where I was going already. Very good. Okay, very good. That is exactly true. You use iron and some kind of acid, dilute acid. It could be a hydrochloric acid or dilute sulfuric acid. Anyway, so we have come to the end of our session today. Okay, somebody has a question for me. Are you going to post this video tonight? I will try to post this video tonight. It's about 8:30. It takes me about 3 hours to process this for posting, but I will post it tonight before I leave. That is correct. I will try. I will do that. Okay, it depends. Well, let me say that I will do my best to post it. But if I don't post tonight, I will post it very early tomorrow morning. Okay, is there any other question? Okay, here's a thank. Okay, very good. Okay. Okay, any other question? Okay, I think it's 8:30 already. We spent about 90 minutes already. So I hope you guys enjoy the rest of your evening. I will see you tomorrow. And so make the best use of the rest of your day.